Today we want to talk about the next level of continuity. There's like a more continuous than continuous. When we look at continuity, our intuition is that we can draw the graph without lifting our pen off the paper. And then we had to have our definition. The function is defined, the limit exists, and those two values are equal. Three things contained in our definition. What we're describing here is how connected the function is. We're trying to describe a graph that is connected. All the points are connected together. So all the points are connected together. One level up from this, once we have established that all the points are connected together, the next level up from this is how smooth the function is, whether the function is smooth or not. And then we can keep going with this and say how smooth is the function. And smoothness is described with differentiability. Our idea behind differentiability, we want to draw a smooth function. The main thing that we're looking for, number one, it is connected. We can't have smoothness without connection. And number two, the main thing we're going to be looking for is sharp corners. So with smooth, we want connected. And we want no sharp corners. This is not a very technical term, sharp corners. The F do I mean by sharp corners? So we should use a more technical term. But what we mean is, oops, I had a meeting yesterday. So. That doesn't show up on the recordings. So we need a more technical term than no sharp corners. So let's use a no pointy bits. Yeah, that's better. So a function is differentiable. First of all, it has to be connected. If a function is differentiable, then it must be continuous. It's like a higher level of continuous. A differentiable function is at a high differentiability. Sentence is hard today. Differentiability is like a higher form of continuity. See what's upgraded I'm going to use modern streaming parlance. It's continuity plus. So differentiability is continuity plus. The specific plus is smoothness. Our intuitive idea about differentiability is smoothness. The thing that we'll be looking for in a graph is that there's no sharp corners, no pointy bits. Sharp corner. Here's our definition of differentiability. Secretly, you already know this one. A function is differentiable at a point if we can find a derivative at that point. So we'll say that f is differentiable at x equals c if and only if. If and only if, very common to use in a definition. F is differentiable at x equals c if and only if the limits as h goes to 0 of f of c plus h minus f of c all over h exists. That is, a function is differentiable just means that we can find a derivative at that, a function is differentiable at a point means that we can find the derivative of the function at that point. That's not part of the definition because we encountered this definition before we encountered the derivative. Well, we're just saying that a function is differentiable means we can find the derivative there. What this means is that we can draw the slope of a tangent line at the point. The idea here is that we have to be able to draw one tangent line. We have to be able to draw one tangent line. So this is what we want to put together with our no sharp corners, our no pointy bits rule. At a sharp corner, we can't draw the tangent line. Because when we put the tangent on a sharp corner, we try to put a tangent there, it just teeters back and forth. And so when you ask, what's the slope of the line tangent to the curve at this sharp corner? It's like, well, I don't know who's sitting on the teeter-totter, right? We're not defining one line. We've got a whole bunch of lines. And that's not acceptable. That's not the tangent line. That's a bunch of lines. So we don't get a function. So the limit doesn't exist. The reason that the limit doesn't exist from a mechanical standpoint is that the slope of coming from zero, words are hard today. I think this is a more coffee problem. Pause. I'll just re-record the audio. I'm just kidding. I will not re-record the audio. That would require like effort and editing. This fits together with our mechanical understanding of a limit. The limit exists because the limit has to be the same from both sides. So if h is coming at 0 from the left side, we're getting one slope. And as h is coming from 0 towards 0 from the other side, we're getting a different slope. Therefore, the limit doesn't exist. Even though the function is coming together at one point, the derivative is going towards different points. That was a lot of words and sign language that you can't see on the video. But if you're worried that I'm going to say that all again and write stuff, I am, probably for the next week, and it's going to be really annoying. Because stuff doesn't get stuck in your head when you hear it once. It gets stuck in your head because you can't get away from it. Which is why secretly I've taken over the audio of all your devices to subliminally play integrations, multiplications, are kind of a package. Contiguously good. I'm just kidding. I missed a few of your devices. I'm just kidding. I'm not taking over your devices. Now that I've said out loud, taking over devices, that I'm being recorded, Mark Zuckerberg's like, oh, what's this? About taking over devices? And then Elon Musk and Jeff Bezos is like, oh, yeah. There's someone listening, and it's not us. What are we talking about? Oh, yeah. If I don't show up for class tomorrow or the rest of the semester, that's what happened. Zuckerberg got me. Sorry, now I'm playing out the scene where Zuckerberg gets me in my office. I open the door and he's standing there all robotic like, Professor Leach, yes? Like in Terminator. I'm sorry, Mark Zuckerberg can't express the level of emotion of the Terminator from the 1984 classic. See, the fun part about punching up is that if these powerful people do come after me, how pathetic would that be? I'm just some schmuck teaching math at a community college, and if they come after me, that's fucking pathetic. So it's like that's why you punch up, because it's sad for them if they respond in any way. Ultimately, they're all sociopaths, so they don't give a shit one way or the other, but they can't respond. What are we talking about? Oh, yeah. So I had to put in some time between saying what we mean by the no pointy bits and then drawing a picture and saying it again. So let's imagine that we have a function. Imagine that we have a function. I'm going to use an actual function, absolute value of x. F of x equals absolute value of x. What does this graph look like? What's the graph of absolute value of x look like? Just a straight line? So if x is positive, if x is positive, then the absolute value of x doesn't do anything, right? It just says, yeah, just keep that number. So we're going to draw a line y equals x. But if x is negative, what does the absolute value function do? It makes it positive. We look at the opposite of what the x is. So we end up getting this V-shaped graph. It's entirely possible that you get to this point in your mathematical career never having seen the absolute value graph, but it's this V-shaped graph. The way we can think of absolute values, we can think about what absolute value does. And so we can define this with a piecewise defined function. We could say that f of x has two parts to it. It does two different things. If x is greater than or equal to 0, then it's just x. The absolute value of 0 is 0. The absolute value of 5 is 5. The absolute value of any non-negative number is just the number itself. But if x is negative, doing this incorrect. So the absolute value function is just the function if x is greater than or equal to 0. But if x is negative, we change the sign. So the absolute value of negative 5 is 5. We take the opposite. So f of x is negative x if x is negative. So there's a piecewise defined function for absolute value of x. The interesting thing about this graph relative to what we're talking about today is the fact that there is a pointy bit. There is a sharp corner at 0. That's what we were going for. That's what we wanted. Pointy bit. This is how I find out if anybody takes their note-taking so seriously, they will not write the phrase pointy bit in their notes. They're like, well, I'm not writing pointy bit in my note. That's why I gave you two options. Pointy bit, sharp corner. So anybody who replaced pointy bit with sharp corner, you're taking your note-taking very seriously. And I can respect that. So what we want to notice is that if we try to find the slope of the tangent line coming from the left, then coming from the left, the slope of the tangent line is -1. The slope is -1 coming into 0, but the slope coming out of 0 is +1. So the slope going into 0 the slope as x approaches 0 from the left is -1. But the slope as x approaches 0 from the right is +1. So there is not one slope at 0. There's not one slope that we can assign at the point 0. There's not one tangent line that we can draw at 0. Anything from a -1 all the way up to the +1, all just is tangent to this function. There is not one slope at 0. We're approaching different values from either side. If we draw a graph of this derivative, the slope as x approaches 0 from the left is -1. The slope as x approaches 0 from the right is +1. Here's the graph of f prime. What we notice about the derivative is that the derivative is discontinuous. This is what's going to be happening at pointy bits. The derivative will be discontinuous. The limit as h goes to 0 of the slope does not exist because we're approaching different values from either side. All this is to say that the function is not the limit of the limit in the derivative does not exist. So the function is not differentiable. The function absolute value of x is continuous. All the points are connected, but they are not smoothly connected because of that pointy bit. Any questions? So absolute value of x is continuous at 0. It's continuous everywhere. But absolute value of x is not differentiable at 0. Casually, we would say f of x, the absolute value of x has a sharp corner at 0, so it's not differentiable there. To sound like we're using the definition, we would say there's no derivative there. The limit doesn't exist. The reason that the limit doesn't exist is that the slope coming into 0 is -1, the slope coming out of 0 is +1. So with the derivative at 0 is undefined. Correct. Because it flattens out smoothly and then it comes out smoothly again. So yeah, x squared does not have a sharp corner at 0. X squared is rounded off at 0. It's smooth. So x squared is connected, so that's the continuous part, and it's smooth. So it's like no corners, no pointy bits. Any question? As far as explaining that goes, it depends on the context, right? So as far as explaining why this is not differentiable at 0, we can all just look at it and say, look, there's a pointy bit. But we also have to think about how far could this go? Like, oh, well, what does a pointy bit matter? Like, let's suppose that we had to take this to court and we're going to be standing in front of Judge Judy on national television. And it's like, oh, well, Judge, there's a pointy bit at 0. She's like, well, what does that mean? And you know she's about to make fun of you because she's like all mad, like all the time. And she's going to make fun of you. And you're like, well, the derivative doesn't exist. She's not dumb. She'd be like, oh, that's saying the same thing. Why doesn't the derivative exist? And you're like, well, the slope going in is different than the slope coming out. And then she'd be like, oh, listen, that's saying the same thing. You're like, oh, fuck. Get off of me. Get all the way off my back. So if you really wanted to bring it home, the limit as h goes to 0 from the left of this ratio is -1. The limit as h goes to 0 from the right is +1. Therefore, this limit doesn't exist. Therefore, the function is not differentiable at 0. QED. Don't say that to Judge Judy. Any questions? Comments? I like to think that if you dropped a mathematical proof on Judge Judy to prove the case and finished it with QED, that she would be like, oh, all right, and like high-five you. I don't know that that's true. I think you probably would just cease to exist at that moment. If you look at you sternly, then the camera would pan over to where you were standing, and everybody's like, oh, well, what happened? And then it would pan back to Judge Judy. She'd be looking at the camera. Then the camera would pan away. It's like, oh yeah, yeah. You know what I mean? Does everybody know who Judge Judy is still? I don't know what's still in like. The other day I made a reference to the fucking Matrix, and I just realized how old that fucking movie was. At some point I made a reference to the Matrix, and I had to stop and think for a second, like, holy shit, that movie is older than almost everybody in the room. Don't worry, someday you'll be older and out of touch as well. Yeah.